Welcome into lecture number 7 in differential equations. This lecture is on numerical methods. So here is the scenario that we're working with now. Let's suppose we have a first order initial value problem. So suppose we have a first order initial value problem. Remember, this is an equation of the form y prime is equal to some function f of ty with an initial value. So it's an initial condition of y of t naught is equal to y naught. Up to this point in the semester, we have studied a number of different ways of solving first order equations, right, analytically. So we know how to solve linear equations, we know how to solve separable equations, and now we know how to solve exact equations as well. But there are still a number of different kinds of equations that we can't solve, and they don't even get names, right? They just don't fit into those bins. So there's a number of differential equations that are not linear, separable, or exact. And for those, we can still try to approximate the solution by using what are called numerical methods. So we can still try to identify and locate the curve of the solution without actually solving for the unknown function analytically. And that's what we're going to talk about in this lecture today. So the first method that we're going to talk about, and the most famous method, is called Euler's method. And this is sometimes also called the tangent line method. So Euler's method. And this one says the following. Basically, what we're going to do is we are going to consider, I'm going to sketch a plane here, a ty plane. And let's suppose that we know that our initial condition is maybe around here. It can be anywhere, okay? But let's suppose it's around here. And what we're going to do is we're going to try to find a number of points that approximate the curve of the solution. So we know for sure that our solution has to pass through this initial point. That's the initial value part of the initial value problem. It must pass through this point, right? The other thing that we know from our first order, initial value problem is the differential equation part of the scenario. And that says that the curve that passes through this point has a prescribed derivative, right? The instantaneous slope, the slope of the tangent line to the solution curve at this point, t naught y naught, is given by this function, right? And so, for example, maybe f of t naught y naught is a number, right, that gives us a slope that looks something like this at this point. So what we can do in the Euler's method here is to approximate this curve. So let's say that we want to find the solution, approximate it on an interval from, say, t naught, from our initial value, in the positive t direction over to, say, some number capital T. Then what we can do is we can partition our t interval down here into a number of points. All right, and this can be done two ways, or at least two ways. One way is you can just pick a step size and get as close to t as you want, or you can say, all right, I know I want to get to this capital T, this value of capital T, and I want to take 10 steps, and you can partition that way. So you can either choose a very small step size, or you can choose how far you want to go, and then the number of steps that you want to take. All right, but the main idea here is that we're going to take evenly spaced steps. So over here, this is where I'm going to summarize the method. Let h be a positive number, okay, that represents the step size. So h is a positive number that's going to represent our step size in the t direction. All right, and what we're going to do then is we're going to iterate. So we're going to start with our initial t value, and we're going to move to the next one. Okay, and the idea now is that if this is t1, all right, so this one right here, this one that I've now made blue, t1 is equal to t naught plus one step, right? So at this point, we can go up from here to the tangent line that we've just drawn, right? So to the tangent line that we've just drawn with our prescribed derivative here. And now we have a new point. And this point sits above the t value t1, but its y value is the question, right? So its y value we'll call y1. That's the question. All right? Now, it lies on a tangent line, or a straight line, I should say, a straight line that passes through the point t naught y naught and has the prescribed slope from this function, right? So at this point here, our line is going to pass through, like I said, the point t naught y naught, and it's going to have the slope prescribed by this. So I'm going to call this slope m, and this slope is going to be f of t naught y naught. Let's call it m naught, m0. And that is exactly the slope prescribed by the first order differential equation. So this point y1, well, if we first of all, let's write down the equation of the of this line, right? I mean, it's tangent to our solution curve, but so that's why I keep saying tangent. But it's just a line, right? So its equation is going to be y equals y naught plus the slope m naught times t minus t naught. All right, and y1 is the point that sits directly above t1, and t1 is t plus h. So y1 is going to be given by y naught plus m naught times t naught plus h, right? That's t1 minus t naught. And of course, the t naughts are going to cancel, and that's just going to end up being our step size. So our new height, y1, is going to be y0 plus the slope prescribed by the differential equation times the step size h. This is our new height y1. And so now what do we do here? We want to get all the way over to capital T, right? So what do we do here? Well, we go back to our differential equation and we plug in our new data. We plug in our new point, t1 and y1. We just figured out this new point, right? So maybe the slope here has mellowed out quite a lot, right? Maybe it looks like this now. All right? And so at this point, the slope, we'll call it m1. So this slope m1 is going to be our function f applied to t1 and y1. We now know what those are, so we can just plug those into this differential equation. We get a prescribed slope, and we can follow that line, right, out h units. So one step, right, h units. The new t value down here, that'll be t2. T2 is t1 plus h. We follow all the same argument that we just got, right? And we'll find that our new y value, which in this case is very close to the old one, the way I've drawn this, right? But our new y value, y2, is going to be the previous y value plus the prescribed slope, right, times the step size, h. And this is the way Euler's method works. And you just continue this until you get all the way over to sit above t, right? So that you're sitting above this capital T that you want. Or if you decided to use a fixed step size and just take, you know, a bunch of steps, then however many you've taken, however many steps you want to take, then you're done with your Euler's method. There will always be error in Euler's method, but you know, it's okay. So we'll study that a little bit more later on. But let me write down the algorithm. So I've drawn kind of geometrically the idea here. So when I said there's going to be error, the idea then, what I'm talking about, is that the solution curve is not equal to that tangent line. It's just, maybe it looks something like this, right? This is the actual solution. And so notice the second you take the tangent line, you're going to stray from the actual curve. Maybe the next one brings you a little closer, but maybe you get further away. And as you move along, there's ways to measure this, and we'll study that, especially in the exercises for this section. Okay, let's write down the algorithm. So this is going to be Euler's method's algorithm. And we've got pretty much everything we need here. We've talked it through. I went pretty fast there, but you can always pause the video, right? So this is Euler's method, the algorithm. Again, sometimes called the tangent line method. But here's the idea. Once again, we have our initial value problem. So let me write this out. So given the initial value problem, it's always going to be first order, but I'm going to write this just in the line here. So the initial value problem is going to be y prime equals f of ty with the initial value y of t naught equals to y naught. All right. The first step is to apply the fundamental existence and uniqueness theorem and make sure that this initial value problem actually has a unique solution, right? So the first step is always to apply the FEUT. And remember the FEUT, we have a general version and a linear version. So we want to apply the FEUT to make sure that this actually has a solution, right? To make sure that a unique solution exists. All right, then the next step, once that's been verified, so once the FEUT has been verified, then the algorithm is as follows. So then, here's what we do. We choose you're either given this or you're going to choose this, but you choose your step size. So choose step size of h greater than 0. Again, it's going to be small, right? And then partition the t-values. So partition the t-values. Now, if you're moving in the positive t direction, then which is usually what we're going to do. We're usually going to start at the initial value and move in the positive t direction, but there's no reason that we have to do that. You could move in the negative t direction if you want. So that'll be an exercise for you guys to modify this algorithm to move in the negative t direction as opposed to the positive one. And it's a very simple change that needs to occur, but you might have to think for a few minutes about exactly how this method works before you can make that simple change. So I'm going to leave that as an exercise for you guys. But we're going to move in the positive t direction. So here's how we're going to do it. We're going to start with t0, obviously, equal to the initial value, right? This is our given initial value. So it's given in the IVP. And then we're going to define t sub k, so the kth entry in the partition, to be equal to t0 plus k times h, and this is for k equal to, and honestly this will work for k equal to 0 as well, right? So 0, 1, 2, etc. Honestly, what we're really going to care about k equal to 1. So let's just start with k equal to 1 there. Even though the formula gives the right answer for k equal to 0, it's not really part of the algorithm. So all this does is it adds h to the previous value, right? It adds an h to the previous value, and that's how you're going to get to your kth step. If we start with the 0th step, the first step is t0 plus h. The second step is t1 plus h, which is t0 plus 2h, right? So that's exactly what we want there. Then the next thing is to compute. So by the way, we can do all the t-values at the very beginning, right? So now, at this point, we have all of our evenly spaced t-values determined. We don't need to worry about those. The big question now becomes, what are the y-values above each of these t-values? That's the question. And the key to computing those is going to be the slopes at each one, right? So we're going to compute the slope. It's very closely related to the slope field that we studied back in a previous lecture. But we're going to compute the slope at every point determined by the initial value problem, and then we're going to update our points. All right? So here's how this is going to work. So we're going to compute the slope for each point. So we'll call this m sub k minus 1. This is going to be f of t sub k minus 1, y sub k minus 1. And this is going to be true for k equal to 1, 2, etc., starting at 1. So now, because this starts at k equals 1, we'll get m0. m0 comes from t0 and y0. That's our first one, right? That's the first slope that we're going to compute. And that comes, again, directly from plugging into the function on the right-hand side of the differential equation. Once we know the slopes, then we can update the y values. And this part has to be done iteratively. So you have to do a slope, a y value, a slope, a y value, etc. Because you have to know the y value to get the slope, right? So you have to know the previous y value to get the slope, which is going to give us the next y value. So that has to be an iterative process. So update the y values, and they're going to be done as y sub k is going to be equal to the previous one, y sub k minus 1, plus our slope, m sub k minus 1, times the step size. All right, and so just like we worked out up here, you just write the equation of the line, everything cancels but the step size in this portion, and you end up with exactly this formula for k equals 1, and then for k equals 2, you get this formula, etc. All right, and so this is exactly the same thing. And again, this is true for k equal to 1, 2, etc. All right, and then you continue this for as many steps as you want. So continue for as many steps as needed or wanted. All right, so this is the basic idea of Euler's method, and this is the key to the algorithm. Before we look at some code and we look at some examples of computing with this, actually computing with Euler's method, let's talk about some of the subtleties. So if we take, you know, a step size and we get an approximation that maybe this is our solution, right? And maybe after this point, we start getting a pretty bad approximation. Maybe it starts to look like this, right? So after we get it further away from the initial value, our curve starts to meander away from the real solution. And of course, in reality, we probably wouldn't know this for sure, right? Because we don't know the exact, if we knew the exact solution, we probably wouldn't be doing Euler's method. But how can we minimize this error, this gap that's happening out here as we got further away from T0? Well, one obvious way is to take more steps, right? And smaller steps. Smaller steps is more important than the more steps, but you want to take smaller steps, which then requires you to take more steps, right? So taking a smaller h will result in a better approximation. So that's one note that we should make here. But taking smaller step sizes results in a better approximation in general. There are always, you know, examples that you can find that maybe something weird happens, right? So I'm going to write a better approximation in general, like I just said. So it's not always true, but it's generally true. All right, so that's important. And obviously this whole process depends on the solution being fairly well behaved in the first place, and really on the function f not breaking down and not becoming either undefined or you know, extremely large where it's untenable to compute it if it's really just huge, right? If it becomes very vertical, right, it's going to pull your points right off the page at this point. So you know, the accuracy also depends on the behavior of that function f. That's what I'm trying to say here, right? So accuracy also depends on the behavior of f near the initial point. All right, so I've talked enough about this. We've drawn a picture. We've written down, you know, kind of a terse algorithm here. So let's do an example. This is one. I'm going to switch to Sage Math, and I'm going to show you how to compute this with Sage Math in a moment. But let's do the first couple steps here on paper. So consider this initial value problem. This one is going to be y prime equals t squared minus t times y. And the initial condition is going to be y of 1 equals a half. All right? And so I want to approximate the solution to this, provided it exists, right? So let's start by applying the FEUT. Remember, that was the first step, right? Before we apply Euler's method, we first need to make sure that a unique solution exists. The reason for this, and we talked about this a lot in the lecture on FEUTs, but the reason the FEUTs are important, right, the fundamental existence and uniqueness theorem, the reason it's important to do this first is because it would be a complete waste of our time to apply Euler's method if either no solution existed or if the solution was not unique, right? If there were many, for whatever reason, if there was a lack of uniqueness for our solutions. So the first step is always to apply the fundamental existence and uniqueness theorem. So let's check it. This differential equation happens to be linear, right? So this equation can be rewritten as y prime plus ty equals t squared. And remember, linear equations have their own special fundamental existence and uniqueness theorem. So in this case, the coefficient function p of t is equal to t. The coefficient function g of t on the right-hand side is just t squared. These are both polynomials, right? And they are continuous at all points in the real number line, right? These are continuous for all of R, the real number line. And so that means that no matter what our initial condition is, a unique solution will exist, right? So the fundamental existence and uniqueness theorem for linear differential equations, which we named FEUT-L, this one applies, right? And a unique solution exists. And so this means that it's not a waste of our time to try to find it. All right, so let's just write down what would we normally do. So we see a linear equation. The first step is then to find the integrating factor, right? So the integrating factor is e to the integral of t dt. So this is e to the 1/2 t squared. That's our integrating factor, right? And then that, obviously, that is a function that does not have a simple antiderivative. Let's see what happens when we plug it in over here. So the solution, the general solution, we can do the particular solution, right? The particular solution is going to be this. It's going to be y of t equals 1 over mu, so e to the minus 1/2 t squared, integral from t naught to t, so from 1 to t, of this function times mu, so e to the 1/2 s squared times s squared, so we can move this around. So s squared times e to the 1/2 s squared ds plus e to the 1/2 times 1 squared over 2. So 1/2 e to the 1/2 e to the minus 1/2 t squared. All right, and so then when t is 1, this term is 0. When t is 1 here, these two cancel, and we're left with a half. This part's good. This part is not, right? This part, the integrand here, s squared e to the 1/2 s squared, this is not an integral that can be done using simple functions. You can try, right? So if you did a u substitution, you might try to make this be the u. You would need one of the s's down here to be part of your du, and then you'd have a square root of this down here, and it just becomes a mess. So at the very least, it would be a mess, right? And at the worst, it's not computable using simple functions that we can write down. You could probably try to use power series methods or something else that you learned in Calculus 2, but we'll get to those later in the semester, so we're not going to worry about those right now. The point is that the solution exists. This is supposedly what it is, right? Not supposedly, this is what it is. You don't have a good feel for exactly what it looks like, though. So we can now use Euler's method to plot the solution, or at least plot an approximation of the solution, right? So because this part right here cannot be integrated using simple functions alone, right? We're going to apply Euler's method to see if we can get a graph of what this curve is going to look like. So I'm going to switch to Sage Math, and we can look at this over there. All right, I have switched over to Sage Math, and I've already loaded some code of Euler's method. This is code that I wrote myself, so I think there is some built into Sage that you guys could use on your own, but I wrote this one for myself. So I'll share this with you guys in the comments of this lecture video. It'll be an interactive page where you can run this code yourself. So you don't even actually have to be able to write this script yourself. But here's what this is doing. So the Euler, that's just the name of the function. It takes in the function f, which is the right-hand side of our differential equation, the initial points, so t0 and y0, those are our initial t and y values. H is our step size, small, right, remember? And then capital N is the number of steps that we want to take. So for this one, I'm giving a number of steps that we want to take. Then what it does is it makes a list of t and y values. So basically it just makes a list of values, okay? The t values, it very quickly just adds h to each one, and adds to the next one, right? So append means add to. So it takes the previous t value, adds h to it, and then throws it in the list, right? The y values it has to do following the algorithm that we talked about, right? So it has to update the slope using that function f, which is the right-hand side of the differential equation, and then plug in the previous y value, add to it the slope times the tiny step size, so the slope that was computed, and then update the y values, and then repeat, right? And then what does it output? Well, it outputs that list of points, so the list of t's and y's, and it also outputs a graph, so it gives us the graph. All right, so let's see how this works. Remember, our differential equation was, let's just go back and take a look at it. Our differential equation is y prime equals t squared minus t times y. So our function f is this right-hand side, t squared minus t times y. All right, so we'll name this. First, we have to name our variables, even though they're in the function up there. But t and y have to get named. Then our function f was t squared minus t times y. Okay. we can name our initial values. Remember, initial conditions were t0 equals 1 and y0 or y0 equals 1/2. So t0 is 1, y0 is equal to 1/2, or I'll use 0.5. And then for this first example, let's take step sizes of 0.1 and let's take 20 of them. So we'll take a full 2 units of steps. So we'll be our solution curve will extend to the t value of t equals 3, right? 2 more units past this one. All right, and so then we want to save this. So we'll call this PP and GG, just why not? Let's call it P1 and G1 because it's our first example. And then we just give this Euler of all these conditions that we've predefined here. And then when we change those later, it'll all be okay. F is not the, oh, I'm typo right here. This should be T, right? Okay, so there we go. So it's now saved the list of points, which we can look at. So there's the points. It starts at 1, 1/2, 1.1, 0.55, and so it's growing, 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 and it appears to be growing the whole time. All right, growing the whole time from our initial point up to 3. So there's, you could just look at that and you can see a little bit about how the function behaves, but it's going to be better to see that graph, right? So let's take a look at that graph, G1. And there it is. So in this window, it's got a little bit of that exponential curve, but it's also pretty straight here, right? Okay, so we can do even better though, right? Because we can take a smaller step size. We could cut this step size down by 10 and then take 200 steps, right? So we can make our h be 0.01 and then our n be 20, or 200, I'm sorry. So let's check that, right? So let's try it. So this time we'll call this P2 and G2. And we will apply our Euler's method to F, T0, Y0, and then I didn't predefine these, but 0.01 and then 200, right? All right, now when we print P2, the list is much longer. All right, so it's much, you have to scroll through it. It's not as illuminating. I mean, it's still doing pretty much the same thing. So we can compare the last value, 2.611. Here it's 2.610. They're going to be very close together, right? So let's then look at G2, and then I want to look at these on the same set of axes, but it would be nice to change the color of one of them. All right, so to plot this curve, which we call G2, I just changed the code a little bit to make it red. So this is the way that we're going to be able to see these together. So we can plot this by itself. So there, that just defined it, and there's the curve itself. So this red one is going to be the step size of 0.01. And if we plot this together with G1, we'll see the difference between the two. And you'll notice there's not much difference. So it's not easy to tell the difference between them. It's even very cloudy, right? But they're obviously very close at the beginning, and that's because that's where our initial value was. We know that that's the tangent to the exact curve. The blue then starts off a little bit lower. Remember, that's the 0.1. That's the bigger step size. And then eventually actually ends up a little bit higher. The red takes a little bit different route, right? It starts a little bit higher in the y direction and then eventually kind of levels off to where it ends up being slightly below the blue one. But in this case, they're both pretty good because obviously they're that close together. That's pretty darn good, right? So this is how you can use Euler's method with different step sizes to approximate the solution to an initial value problem that you can't actually write down the solution to, other than to just write down so this is how you use Euler's method to approximate the solution to an initial value problem that you can't write down the solution to, other than to write down just the integral formula itself, which we wrote down the integral formula right here. So there's an example of Euler's method. Now, for the rest of this lecture, what I'd like to talk about are ways to improve on Euler's method. And we're going to talk about two different ways to actually do that, to improve Euler's method. The first way is literally called the improved Euler's method. So in this class, we won't get into the details of why exactly it does, in fact, improve the results of Euler's method. That we'll leave that for a later course, maybe a second course in differential equations or a different future course. But I just want to give you kind of the heuristic kind of layout of how the improved Euler's method works. And then there's one more method, and we'll do an example with all three of our methods together. So first, we'll have improved Euler's method. Let's draw a picture again. So this time, I'm going to define this almost exclusively from the picture. So we've got our T naught. We now understand the problem, right? So we have our T naught and our Y naught. We want to try to approximate, a couple steps here. I'm just going to draw the next one. Let's call this actually TK, YK, and TK plus 1. All right, actually, let's do TK minus 1 and then TK over here. So this will match up exactly with what we have in our formulas up above, right? So the idea is we want to use this point that we know, whether this is the initial value or just a previous point in our approximation, we want to use this known point to approximate the value of our solution curve over the next point. So we still have the same situation, right? We have our y prime equals f of ty. We have our y of t naught is equal to y naught. We have applied our fundamental existence and uniqueness theorem, and we are now approximating the solution, right? So we can do pretty much the exact same thing, which is compute the derivative, right? So the slope of this line, we'll call this m. We already used m. So let's call this r1. And so this r1 is going to be the slope of f, the slope determined, right, by this point on the left. So it's f of tk minus 1, comma yk minus 1. All right. And then what we'll do is we'll follow this line determined by this over to sit directly above tk. So that's one full step, right? One full step, which is our step size h. And at this point, now we can plug this point. Now we have a y value, right? So up here, it'll be somewhere up here. This will be, we can call this like y hat k. And this is going to be yk minus 1. This is what we get from our Euler's method, right? This exact point. So then this is the, plus r1 times h in this picture. But over here, at this point, now that we have this point, we can plug this into our function as well, and we can get another slope, right? So maybe the slope has mellowed out up here. It's still positive, but it's not as, the magnitude is smaller. And so the slope of this one is r2. R2 is going to be f of tk, right? F of tk, which is, by the way, tk minus 1 plus h, right? But this is f of tk, and then yk with a hat. Yk with a hat. And then what we can do is we can come back over here. We can pull this slope back over here. So how do we do it? Well, we just take this slope and we apply the same logic that we did over here, but we apply it with this slope for r2 instead of r1. And then we follow this point out till we get directly above tk. All right. Now, this point up here, we already said that's yk with a hat, right? We'll call this one the y value of this. Maybe, oh, it's a little above that, right? It's like right here. This one we can call yk with a squiggle. And this one's going to be what? Our previous one, so yk minus 1 plus r2 times h. All right? Which one of these is better? Which y value is better? Well, I mean, that's the one that we got from the Euler's method before, but we noticed that when we plugged in, we get this different slope, and we carry that over. That's a different point, right? So it's not, we can't really say which one of these is exactly better, quote unquote. So what we do then is we take the average. And so we update, our update is this point. So our update is going to be that yk plus 1, no, just yk, right? So just yk. Got myself confused with the notation, but yk, so that's the point above tk. Yk is just going to be the average of these two. So it's going to be 1/2 of yk bar plus yk squiggle. And one of those is just Euler's method. The other one comes from taking the slope at the point from Euler's method, pulling it back, and then extending forward from there. And this is the improved Euler's method. All right, so all of this, there's an algorithm for this, and like I said, we'll look at code in a few minutes after we talk about the next method. But the idea here is exactly the same. Okay, so this is exactly what we want to do here. So you take one step, you draw back the new slope, you take a full step, you now have 2 points over here, you take their average height, and that's going to be the height that we use in the update. So the actual height, the actual point that we use is this one, and then we continue this on the next one. We get a little spray, right? At every step there's a little, triangle, and we take the midpoint of that base of the triangle in some sense. All right, so that is called the improved Euler's method. Like I said, we'll get into this much deeper in a later course, but that's the algorithm, and we can use it in this course and just believe that it's going to work, and then we can study it in more depth in a later course. So the last method is called the Runge-Kutta method. And the Runge-Kutta method works as follows. All right, so for the Runge-Kutta method, I'm going to zoom in even a little bit more. So in the previous one, in the improved Euler, we used 2 points, right? Two slopes to get a better approximation. In this method, we're going to use four slopes. So again, let's say that we have our yk minus 1, tk minus 1 here. So there's our initial point again. It doesn't always have to look like this, but just for the sake of the picture, here's what we want to be working with. So there's our tk here. And the first step is to do the exact same thing that we've been doing. So you take the slope at this point, and this slope, this time I'll call this one k1. I'll color code it over on this side. So k1 for this slope is just going to be, we're just going to plug into our differential equation, our right-hand side, same story, right? Tk minus 1 and yk minus 1. We'll get a value. That'll be our slope k1. But this time what we're going to do is we're only going to take a half a step out. So we're just going to take this out a half a step. And so now we're going to be sitting above the midpoint between tk minus 1 and tk. So actually the value of this point is tk minus 1 plus a half of a step, plus half of h. All right? And so at this point right here, I want to measure a new slope. So I'm going to measure a new slope here, and I'll do this one in magenta. So maybe it's this. And this slope is going to be what I call k2. So k2, and maybe I need more room over here, because k2, I now need room to write out, it's going to be our function f applied at this midpoint. So tk minus 1 plus a half a step, right? And then it's going to be applied at this point up here in the y direction, which is not, it's not exactly similar to what we've been doing so far, because that's only half a step as well, right? So we've only taken half a step in both cases. So this is going to be yk minus 1 plus the slope times half a step. So plus 1/2 h times k1. That's the slope of the first one, right? k1. All right, so there's our second slope. It comes from measuring right there. Now we're going to pull this back, and it's supposed to be parallel. So pretend that this is exactly the same slope that's right here. We're going to pull this back and follow this one out half a step as well. All right, half a step as well. And this one I'll do in orange. And maybe this one's in between somehow. You're going to have to pretend that my drawings are parallel, but this one, suppose, is in between. So this will be k3. And it's the same idea, okay? So k3 is evaluated at the half step, so tk minus 1 plus 1/2 h. And then at the height of yk minus 1. So we went all the way back to yk minus 1, and then we added half of a step of k2. So 1/2 h times the previous slope k2. So we measured our slope, we took a half a step, measured the slope, took a half a step, measured the slope. Now we're going to take a full step. All right, so this time on the green, or on the orange here, again, pretend it's in between, we're going to take a full step out. And so this one, we're going to measure the slope over here, and this will give us, now it doesn't matter what it is, but let's say it's like more drastic, like this, right? So this will be k4, and k4 is going to be f of, at this point it's tk, All right, so there's a full step. So it's tk minus 1 plus h if you wish, but that's a full step, right? So tk, and then y, k minus 1 plus a full step, h times k3, the previous slope, right? k3. So the previous slope is k3. All right, so this is the picture. Now we have these 4 different slopes. They're measured, 1 here, 2 of them here, 1 of them over here. And we need to weight these now. So the ones that are done in the middle need to be weighted twice as much as the ones on the end. All right, because they're only a half step and not what we would consider a full step for each of these. So our slope in this case is a weighted average. Our slope m, mk minus 1 is what we've been calling it, right? So mk minus 1 is now going to be, since these are half steps, we need to double them. So this is then going to be k1 plus 2k2 plus 2k3 plus k4. And then for this to be an average, we need to divide by the total number of these. And there's now 6 of them, right? Because 1 plus 2 plus 2 plus 1. So it's 1/6 of all this. And this is the new slope that we use to update. And so this slope, whatever it is, let's say it's somewhere in between, right? I don't know, maybe like that. So close to that one, but it's just by chance, right? But this slope right here, this is used to find the true new updated point. So yk is equal to yk minus 1 plus this value, mk minus 1, times the full step h. All right, and that's called the Runge-Kutta method. So the Runge-Kutta method, again, this is the geometric picture that you get, right? But the Runge-Kutta method is analogous to Simpson's rule for approximate integration that you learned in Calculus 2. This one, where you have a left endpoint and a right endpoint together, this is like analogous to the trapezoidal rule. So the improved Euler's method is like the trapezoidal rule, and Euler's method by itself is like the left endpoint rule, right? So if you think back to your approximate integration methods from Calculus 2, we have Euler's method, left endpoint. We have improved Euler's method, trapezoidal rule, right? And then we have the Runge-Kutta method, which is like Simpson's rule, okay? So again, the key here for all of them, the only thing that's different for these is how you update the slope, right? And so Runge-Kutta updates the slope by this more complicated method. Here's the updated slope on this one. So I didn't write it out exactly how the slope is updated, but it's just the average of R1 plus R2, right? So on this one, mk minus 1 is 1/2 R1 plus R2 for these. So that's how we update the slope on this one. And yeah, so those are the 3 methods that we need to know. So let's end this lecture by doing an example of computing with these things. So it's important to know how they work and then to be able to actually compute with them. So this is our last example. Then we'll do this in Sage Math again. So you're not expected to do this by hand in general. The whole point is to use a computer. So either some kind of mathematical computing language, or you could even do this in a spreadsheet. You just have to be careful how you lay out your cells and just make sure everything is organized there. But here's what I'd like to do. So I want to check all 3 of these methods with this differential equation. So y prime equal to y squared plus 2ty divided by 3 plus t squared. Initial value is y of 0 is equal to 1/2, 0.5. And then I want to do this in 2 step sizes for each of them. So 0.1 and 0.05. All right. So before we go to our Sage Math cell over there, our Sage Math notebook, we first need to make sure that this differential equation, this initial value problem, has a solution, right? So this equation is nonlinear. So for this one, we need to apply the FEUTG, the general version, right? And so the general version says that we need to take a look at this function on the right-hand side, f of ty, and we need to make sure that our function is continuous at this initial value, right? And the only thing that could go wrong with this function, it's nonlinear, but it's a rational function, and the only thing that could go wrong is the denominator, right? So in this case, we need to make sure that t is not equal to plus or minus root 3. Actually, no, that's going to always be positive. There's no way for that to be 0, right? I was going to say 3i, but yeah, this is good. So this one is fine because 3 plus t squared is good. So the function itself is fine. And then we need to take the partial derivative, right? So we need df by dy. But when we do this, the y are treated like constants. Or sorry, the t's are treated like constants, right? And so the derivative is just 2y plus 2t over 3 plus t squared. And of course, that's going to also be okay, right, in the denominator. So there's no t values or y values that make the denominator 0 in this case. So these are both continuous. And again, they're both continuous at the point that we care about, right? So they're both continuous at 0 and 0.5, 0.5 at that point. But the FEUT tells us it's worth our time to try to perform these methods, right? All right, so let's then go back to Sage. All right, so I'm back in Sage, and if I scroll down here, you can see that I've also preloaded in the improved Euler's method and Runge-Kutta method. They're very similar to what we did for the Euler's method itself. The updates, though, so in this one I called these M1 and M2, but the updates come from the updates in the slope, right, come from calculating these intermittent points. So it's exactly what we talked about in the picture. It's easier to see in the picture, but you can compare this code with the picture if you want, or the pictures that we drew, and make sure that they're actually doing the same thing. Same thing for Runge-Kutta, more complicated in the updating of m. So finding that slope m is the more complicated piece for each of these. All right, and so you can see this one's weighted m1 plus 2m2 plus 2m3 plus m4 divided by 6 then. All right, so we are going to use all of these. Again, we need to define our function. So let's remember what that function was. It was y squared. Let's go back and look. So y squared plus 2ty over 3 plus t squared. So y squared plus 2 times t times y over 3 plus t squared. So there's our f. Our initial value is now t naught equal to 0, and y naught is still a half, but let's type it back in. We're going to take first a step size of 0.1, and let's do n, capital N, equal to 20 again. So we'll step out from 0, so two full units. Let's go 30 steps. So 3 full units. So this will go to a t value of 3, and then we can see how these all compare. All right. So here's what we're going to do. We're going to write p. We're going to call this p, e, and g. And by the way, these functions give out the same list of points and then graph, right? And these ones are different colors, so we don't have to worry about this as long as we do the same step size. So p, e, g, e. This one's going to be Euler of f t naught y naught h n. All right. And then pi, here's what I'm going to do. I'm just going to copy this, and we're going to make this improved Euler be I and the Runge-Kutta be R, or RK. All right, so we'll call this, you can't call it pi. So PIE, pi is the number pi, right? So GIE, improved. And I said I was going to copy this, and then I didn't. So there's our improved Euler. And then we're going to do Runge-Kutta. Make sure you name it the same way. So underscore Runge-Kutta. And so we'll call this PRK and GRK. All right, it computed them no problem. It's just, it doesn't even take hardly any time, right? It's just a little blip. We really want to see what these look like together, though. So we want to look at their graphs. GE plus GIE plus GRK. And so there's the graphs. And notice now, one of these is not like the others, right? So the Runge-Kutta method is the green. The improved Euler is red. And you can zoom in a little bit. It's hard to see that it gets fuzzy when you zoom in too much. But you can see the red and the green are very, very close together. And the Euler's method, not so close. So if we believe the claim that that improved Euler and Runge-Kutta are better than Euler's method, then you can see it right here, right? The evidence of it. So the actual solution is probably going to be closer to the red and the green here. And the blue curve, which is the Euler's method, does a good job over here. So it does a good job from 0, I mean, depending on how you measure good, but it looks a lot better over here than it does over here, right? So over time, as we get further away from the initial value, the improved Euler's method and the Runge-Kutta method do much better over a long time frame, right, than the Euler's method itself. All right, so the other thing that we wanted to do was try this with a 0.1, right? So let's see how those do. Took just a bit longer to compute that. But now when you compute, you can see that now what happened? Well, the green and the red are like right on top of each other. You can't even see the difference. The blue's been pulled up, right? It's doing much better, but it's still it's much better than it was. So it deleted the old picture when I created this new one, but it's doing much better than it was before, but it's still not as good as the Runge-Kutta and the improved Euler's method. All right, so Euler's method by itself is not bad. Like I said, there's an exercise in your text and your recommended exercises that helps you understand the error involved in Euler's method. And improved Euler and Runge-Kutta, we're not going to study in any more depth in this course, but they exist, and we'll be able to compute some things with them. So we'll just use them and believe that they're good enough for what we want to do in this course. But you'll study those again later in another course. All right, I'm going to leave this lecture here, and I hope you guys enjoyed this. This is very interesting stuff. This is probably more like what you're actually going to be using this class for in your actual studies, or once you're done with this course. So this is kind of like applied numerical methods, right? You're actually finding the curves, finding the solution curves, and approximating values of things above certain points without being able to actually write down the function, and using computers to do it, right? So I will post a link that has a interactive notebook with these exact code snippets. You can mess around, change the functions, run your own code, and see how this works for you guys. So I'll leave this one here and see you guys in the next lecture.